Okay, good afternoon again. Today we're going to finish zero current switching resonant buck converter. Right, as you can see from the screen here, I have the week 5 agenda. So first off, today we'll finish ZCS resonant buck converter, and then we will go into the second converter, ZVS, zero voltage switching, so that you know the two different examples. So one is the zero current switching, the other one, the second one will be the zero voltage switching. Right? So you see the difference between the two. And then for zero voltage switching, the learning outcomes will be the same as ZCS. We're going to go over the circuit, right, and then analyze the 4 different states, and then we'll focus on how zero voltage switching is achieved, right, and then we'll look at the critical waveforms, mainly the resonant capacitor voltage waveform and resonant inductor current waveform. Okay? And then we'll look into critical times on these waveforms, right? Namely the time at which the circuit changes its state from one state to another state, right? And then we'll look into the exact equation for obtaining the average output voltage, and finally the graphical method to approximate the average output voltage. Okay. And for ZVS, I'm going to go through the second converter faster than how I did it for ZCS, okay? Because this is going to be the same kind of concept and approach as the ZCS, right? Any question on this week's agenda for the lectures? So hopefully we'll be able to finish ZVS on Thursday. I'm hoping, we'll see, I didn't put on the agenda, but we'll see if we can have the time to start the isolated version of soft switching. Okay. Secondly, we have weekly assignments. It's friendly reminder that you have 3 assignments. Lab number 3, lab report, due this Friday, 11:59 p.m., upload to Canvas. And for this week's lab, my plan is to for you to look into the effect of leakage inductance to leakage spike. We'll talk about this more in the lab. And then study the effect of snubber capacitance to effectively reduce leakage spike. Those are the 2 main goals for today, this week's lab. And then we also have homework number 4 due this Friday, 11:59. So everything's going to be 11:59, as I announced last week. Upload to Canvas. And then quiz number 4 due this Friday, 11:59 as well. And I strongly encourage you to do the practice quiz to ensure that all the figures are showing up properly. Also the equations. Right? And then for quiz number 4, the problem is going to be on zero voltage switch resonant buck. So the topics that we're going to start today. Okay. All right. Any question on the weekly assignments? All right. Last item. So I look into the transformer selections again after 2 weeks ago, I believe. I think Crystal and Andrew we were working together on finding the transformer, commercially available transformer for the project. And looks like for this type of, if you are using isolated topology, and let's say you are in need of finding the transformer, well, yeah, I should say because you are using isolated topology, then therefore you're going to need a transformer to do this. And if, let's say that your design calls for high voltage transformer, meaning the primary winding will have large voltage, in a matter of in a scale of like 1,000 or more type of voltage rating, then most likely you're going to need they call it a custom-made transformer, right? So what I've decided to do is for you to still choose commercially available transformer, but don't worry about voltage rating. So we can ignore the voltage rating, but you need still, just for, I think it will be a good practice for you to go through for this project, is to still consider the inductances, right? As you can see from here, from this equation, and you also learn it from 212, that the transformer's turns ratio is a function of the primary and then secondary inductances, right? So primary to secondary turns ratio is equal to the square root of the primary inductance of the transformer and the secondary inductance of the transformer, right? And also the type is also important. If you are using flyback as the topology, then make sure that you choose only a flyback transformer, right? I mentioned in EE411 that flyback transformer is different from push-pull as well as forward, right? Because in a flyback, you want the transformer to be able to store energy, right? Unlike push-pull and forward. In push-pull and forward, as well as bridge, the transformer is being used to transfer energy, not to store energy. But in flyback, it is specifically used for storing energy, like an inductor, basically. All right. So yeah, still consider the turns ratio, of course, right, which would be depending on the inductances and also the type of transformer. But you can go ahead and ignore the voltage rating as well as the cost. So do not include the cost of the transformer in the total cost requirement. Remember, the requirement is the total cost should be less than $50, right? So that's not going to be, that does not include, or do not include the cost of transformer, okay, in the bill of materials. And here's an example of a data sheet of transformer, right? So you can see that yeah, we were having problem finding, let me use marker here, finding high enough voltage, right? If let's say you're using it for high voltage transformer, right? Let's say thousands of volts into low voltage, right? So very hard to find this rating that would work well for our design. Again, if you are using isolated topology. So that's why I said earlier to ignore this, right? Ignore the voltage rating. However, you still have to pay attention to the inductances, which will give you the turns ratio, right? For example, here, oh, that's not it. Right there, inductance, right, from 1 to 3. That means from winding 1 to 3. So from here to here, right? So the inductance is from there to there, which you can use as a primary side. That's going to be, what is it, 1.5 millihenries, okay? So you still have to consider this. And then the type also, I don't remember what type this transformer is. It might be a flyback, I don't know. But yeah, you should be able to get those different type of transformers as well as the inductance, right, of the transformer. And then you have the turns ratio right here, right? From 3 to 1, so from here to 8 to 7. So transfer function from these two windings to this winding right there. That's going to be 3 to 1, and so on and so forth. Okay. Any question on this? I'll talk more about this in the lab when we go over your final project, maybe next week. Any questions on this for now?
I had a quick question.
Go ahead.
If the data sheet doesn't specify the turns ratio, can you predict it if it gives you the two inductances?
Exactly. It could give you in terms of inductances or turns ratio, right? You still have to have the inductance though, because that would determine, that's why I'm suspecting this is a flyback, because for a flyback, you need a minimum inductance. That's why it specifies inductance as well, right? But in case it doesn't give you the inductance, in which case I would suspect that would be for forward as well as push-pull, then it's just going to give you turns ratio like that, right? But again, for a flyback, you're going to need the inductance. And then based on the turns ratio, then you can find the other inductances, right? Using the equation I showed you earlier. Does it answer your question, Nick?
Yeah, thank you.
Okay. Any other questions? No? Okay. Now let's finish our ZCS right there. So we already analyzed the circuit, right? Mostly using KVL, KCL, right? That's all we needed for this circuit, this KCL, KVL. And then we found out that this is a buck converter from the equation that we derived last week, right? And then we have the 4 states, right? One of the state is resonant, right? Resonant state, that's the resonant state right there, right? Where waveforms on the inductor and capacitor are sine waves, right? Right there, right? So sine wave starting from here, from that point. And then also sine wave, no, actually, no, not from that point. That's the wrong point. Sine wave starting from this point right there, right? So here's sine wave right there, is also sine wave. And then we wait until the sine wave voltage across the cap goes to 0. No, sorry. we wait until the current through the inductor, there you go. The current through the inductor, resonant inductor goes to 0, right? And then we wait. And then as soon as the current through the inductor, which is the same as the current through the switch, is equal to 0, then that will be the perfect timing for us to turn off the switch, as you can see from here, right? So we turn off the switch at 0 current, okay? That's what we get from this topology. Right? And then we talked about when the peaks occur, right? Peak of the capacitor voltage and peak of the inductor current. We talked about that last week as well, right? Another thing is that we also learned that all these timings, critical timings that we have, you know, T1, T2, T3, T1, T2, T3, those are dependent on output current, right? As you shift or change output current, then those times, you know, T1 through T3 will also change accordingly, right? So we talked about that last week. Another thing that we learned from the circuit is that the average output voltage, right, is a function of load current. It's a function of I out, right? It's a function of this right here. So as soon as I out changes, then average output voltage changes as well. And then we learn from the equation that in order to regulate the output voltage, what do we do? What do we do? As output current is changing up or down, right? If let's say you want output voltage to stay constant, what do you need to do?
Adjust the frequency.
Adjust the frequency, very good. That's the fundamental difference, right, between this topology and the standard buck converter that you learn in EE411. In EE411, you don't change the switching frequency because it's PWM, right? It's fixed frequency. You change the on time, right? You adjust the conduction time of the switch to change duty cycle. Here, in order to change the duty cycle, you change the frequency, right? Therefore, this is not a PWM type of converter, right? So do not use any PWM chip or controller for this topology. It's not going to work. Okay? You need one where you are able to adjust frequency, okay, instead of on time. Okay. Now, another thing that I would like to, which I didn't discuss last week. So let's see if we can answer this question. So pay attention. So one more question I have for you. Let's see if we can find out. All right. We know that the resonant occurs right at that point, right? T is equal to T1. So that's when we have sine wave right there, right? On the inductor current. So focus on inductor current only, okay? Just focus on this waveform only, right? Now, can you tell me, let's see if you can answer this. Can you tell me when, for this converter to work, right? Can you tell me the condition for this circuit for us to be able to do the zero current switching? I don't think I'm asking you to, oh, well there, hang on, let me formulate the question again. By looking at focusing on this, just focus on this, nothing else, just focus on that. can you tell me, let me try to ask it differently. Can you tell me under what condition we will not be able to turn on this, turn off the switch at 0 current? There you go. I don't know if that's
the diode has to be able to turn on. Oh wait, so the diode, the flyback kind of diode, does that only turn on under that condition that you specified? And you're asking what condition will that be met?
Well, yeah, I mean, last week we learned that we can only turn off, right? Turn off the switch right after the inductor current reaches 0. See that? Right? You cannot turn off the switch before that because that's not going to be 0 current. Remember, inductor current is the same as switch current. So if inductor current goes to 0, so is switch current. So therefore, in order for us to take advantage of these waveforms, right, of this circuit, I'm going to have to turn off the switch after inductor current goes to 0, right there. Right? So that way we get 0 current switching. So my question is, just from focusing on the one that I circled right there, can you find us the condition at which I will not be able to turn on, or sorry, turn off the switch at 0 current?
Wouldn't, so like basically if the inductor is not large enough, then like the time that you would need to keep kind of the switch closed for to sufficiently charge the inductor would like exceed the resonant period or something like that? Or would that have to do with it? Because you can't just leave it on as long as you want.
Yeah, let's say I'm turning the switch off at the same time right here. Let's just say I'm going to turn off the switch at the same time, right? Like that. And then under, there's going to be more than one, but I'm looking for the answer that we have not talked about last week. Under what condition, if I turn off the switch at T2 right there, under what condition I will not get 0 current switching? That's my question. There are 2 answers to that.
I don't know. The best I'd be able to do is like an intuitive one. I can't think of like a numerical one.
No, that's okay. It's just based on the waveforms. Based on the waveform that you see there. At what condition do you think I will not achieve 0 current switching? If I want to turn off the switch at T2, same time, right there. Don't change that T2.
If it remains sinusoidal.
Right. That's number 1. That's actually the answer I'm looking for. What's number 2?
If you lower the resonant frequency of your LC circuit, that's going to stretch out.
That's correct. Very good. Very good. All right. So the second answer, that's what we learned, right? The resonant frequency has to be timed perfectly, right? Because otherwise, if it's too long, like this, I'm sorry. If the resonant period is too long, or not too long, but not the right value, then if you want to turn the switch off right there, then you can see it's not zero amps, right? So you have a different sine wave that takes longer, meaning the resonant period is longer, right? That means that's not going to work, right? But the answer I was looking for, which we didn't discuss last week, was the first answer. Is that if this right here, this waveform, focus on that waveform, if that waveform continue its sine wave, right? For example, if I'm not careful, then this sine wave is going to bounce back. Let me try to draw it. Like that, right? If let's just say I'm not careful, then that sine wave will start to bounce back up, right? So then what will be the limiting factor of that? What would determine whether or not this sine wave will be or will not be bouncing back? What determined this?
Amplitude, right? Because it's oscillating about the load current.
Exactly.
And if the amplitude is less than the load current, then it won't reach 0.
Perfect. Very good. Very good. Very, very good. That's a very good analysis. That's what I'm expecting you to be able to do. Be able to analyze the waveform and then determine, hey, look, if that peak value right there, that's the peak value of that sine wave, right? If that peak value is more than I out, or sorry, less than, I should say, right? Less than I out, then you're allowing that sine wave to bounce back. So let me repeat. Let's see if you agree with me. If peak of the sine wave is less than I out, then do you agree with me that the sine wave is going to bounce back and you would never ever achieve zero current switching? In fact, you're going to have a sustaining sine wave, right? If you do that. Do you agree with me on that one?
Why does it bounce back under that condition?
Well, because the peak is less than I out. Look at this right here, right? That's I out right there. I out is our offset, right? So you have a sine wave that is riding on an offset. And that offset is I out, right? And now you're going to draw a sine wave on top of that offset, right? So if the sine wave that is riding on this offset, right, this peak value, right? Let's call it X. If that X peak value of a sine wave less than I out, wouldn't that means that when it goes down, it will still above zero, and then you allow it to bounce back right there? This is the 0 amps right there. Do you agree with that assessment?
Oh, you're saying
Well,
under
if
the
I out minus X is greater than 0, then it will bounce back, right?
Yeah, so that means if X less than I out, that means what? That means 0 is less than I out minus X, or I out minus X is larger than 0, right? That's the same thing mathematically. But just use a graphical way of trying to understand this, right? Do you understand what I just draw here? Let me redraw. Let me just draw it on this one. But if you have, don't worry about our circuit. If you have, oh gosh, if you have a sine wave, right? And then let's say that I'm introducing an offset to that sine wave. Let's say this offset is I naught, right? And then let's draw our sine wave above I naught. Let's use red, right? And I could draw it this way, right? Can I, right? So that happens when what? When the peak value right here, X, call it X, is less than, isn't it? If
that would
X,
be greater than, wouldn't it?
oh, sorry, greater than, oh, hang on. Yeah, X greater than, yes. X greater than I out. Did I write it wrong earlier? Maybe I did, sorry about that. So you can see that if the peak of the sine wave, I call it X, is larger than the offset, I naught, wouldn't this, when it goes down right there, wouldn't it reach 0 and then try to go negative right there? You agree with that statement? Yes or no?
Yeah.
So that's case number 1. What if I do case number 2? X is less than I out. What's going to happen with that sine wave? The same offset, but now the peak of that sine wave is less than I naught. Wouldn't it go something like this? That's your X right there. Do you agree with that?
Yeah.
Okay. How about the rest of the class? Is that okay? Is that clear? Yes?
Yeah.
Okay. So
Just a quick question, I guess, for my own clarification. So you're just saying, Professor, that the peak has to be greater so then it can touch 0, because if it's
Correct.
less, then it won't hit 0 and it'll just keep going sinusoidally, right?
Exactly. And that's the key for zero current, right? We want to deliberately have the sine wave to hit 0 and try to go negative, right? Because we have, the unidirectional switch, we clamp that current to 0. So this is the perfect time for us to turn the switch off if it hits 0 and stays at 0. Whereas if you have case number 2, if I call it case number 2, right, where the offset is larger than the peak of the sine wave, then this sine wave will never reach 0, right? It would never reach 0, so therefore you would never get ZCS.
Can I ask a quick question?
Yes.
When it doesn't hit 0, is it oscillating back because we're technically waiting for it to hit 0? Or does
Yeah.
it not hitting 0 have some consequence in the circuit that makes it bounce back?
So because the way we have the circuit, right, the circuit only allows positive current. So this is still positive current, right, through the inductor. So what's going to happen is that it's going to keep oscillating like that. So you're going to have
it's like okay.
Yeah, exactly. So the circuit would never change its state from resonant to state number 3. It will just remain at a resonant circuit, as a resonant circuit. So basically the circuit's not going to work. Does that make sense? Yes?
Yeah, that was the piece I was missing. Thank you.
Okay. So I just want you to be clear that, right here, that it is important for us to have that condition met, right? That our, is this the right statement? I peak sine should be less than I out. That's correct, right? That the peak should be less than, no. Should be larger, isn't it? Larger. Yeah, the peak should be larger. So sorry, that was wrong. So the peak of the sine wave should be larger than the offset. If the peak of the sine wave is larger than the offset, then it will guarantee that we can get the zero current switching. Right, so this means I peak sine minus I out is larger than 0. Excuse me, larger than 0. Right? Now, why is that important to know? Well, again, we want this circuit to work, right? And we want to be able to size the components properly. That's kind of this. That's the section that I unfortunately don't have yet, sizing the components. But keep in mind, if you want this to work, then this condition has to be met, right? When you're actually designing this circuit, you would know I out, right? That's going to be based on I out max, right? So eventually it's going to be I peak sine must be larger than I out max. When you're designing a converter, you will know what I out max is, right? You will know the maximum current through the load is, right? From maximum power. We talked about it in EE411, right? So you will know that value. You will know this value. But what about this value? How does this value translate into component values? Well, that's why we went over the equations last week, right? Do we have the equation for IL? Because that's IL, isn't it? Yes, we did, right? We had the equation for IL in the second state. So let me go over that section right there, or right here. That's which one is our resonant? This one, right? So right here, this is the state that we are looking into. I want to know the peak value of this inductor current, right? Well, we already had, we derived the equation for that current, which is right here, coming up soon, right there. Okay, you can see clearly that we have a sine wave that is riding on top of an offset. That's a constant value, as we talked about, right? So therefore, what is the peak value? What is that I peak sine? Remember I wrote earlier, I peak sine must be larger than I out max, right? Average value. Can you know what I peak sine is from this equation?
VS over ZO.
Very good. So this translates from this equation. Now we know that I peak sine is VS over Z naught. Has to be larger than I out max, right? Again, this is not in the book. Go ahead and write it down in your book. Something that I have to add in the future EE411 book. So then let's take a look at VS over Z naught, right? Do we usually know what VS is when you're designing a converter? The answer is yes, right? That's a supply voltage. That's a source voltage, input voltage. So you typically know what that is, right? What about Z naught? Well, Z naught is, as I mentioned last week, that's the characteristic impedance of the resonant circuit. That's going to be L resonant over C resonant, right? Square root of L over C. So this is the design aspect of this converter, is that when you designing this converter, make sure that Z naught, which is the square root of LR over CR, right, that goes into here. When you do this calculation or design selection, make sure that the entire value, the ratio of VS over Z naught, must be larger than I out max, right? So how do you pick LR and CR? Well, one equation, two unknowns. So you have to pick one and then get the other, right? So I would say you probably select L, right? Just choose L, right, from the commercially available values. And then from there, you can calculate or solve for CR, right? So once you choose L and then you calculate CR, wait, VS is, okay, we can just do it this way. And then, so therefore VS over I out max is larger than Z naught, right? Am I right? Yeah. From this equation, I know VS, I know VI out, right? I know VS, I know I out. Then now, if I go to here, then you know that VS over I out max must be larger than square root of LR over CR. Okay, so this is going to be a value, going to be a constant value. So as you are, after you choose L, right, then you can calculate C to meet this requirement. Does that make sense to you? Any questions on this? Okay. Once you choose,
Sorry, which page is this on? I'm kind of having a problem finding in the book.
It's
Where-
on page 85.
Oh, okay.
yes.
Thank you.
Sorry about that. Yeah, 85. I should have mentioned that. Okay. Any question on this? If you didn't get a chance to write this down, go ahead and capture screen. So you have this recorded in your computer, and you can transcribe that into your notes, into your book later. Okay. So this is a very important design aspect of this circuit, right? When you select L and C, it has to follow this criterion. Any questions? Okay. If not, let's move on to examples. I've not gone through the examples yet. Let's see. Right, so we derive these equations, right? Instead of, so we have two different ways of getting output voltage. Sorry, let me go back. Page 89, right there. You have the exact equation to find the average output voltage. Right? Or we can approximate average output voltage by deriving the equation so that you have relationships between the ratio of the frequencies, in this case, switching frequency to resonant frequency, with respect to the ratio of voltages, output voltage over input voltage, as a function of the ratio of the load resistance to characteristic impedance. So that's what I derive right here, right? Long derivation. As you can see, I spent a good day to derive this. And then at the end, this is what I want you to see, is that I could relate the ratio of the frequencies to the ratio of the voltages, right, to the ratio of the load resistance and characteristic impedance, right? So this is something that I could plot, right? You can see that the ratio right here, the ratio of the frequency is a function of the ratio of the voltages per given ratio of RL over Z naught. So this is the given value, right? So if you plot this, then you get family of curves, right? At a given ratio of load resistance, and characteristic impedance. So every single one of these numbers right there, 0.5, 1, 2, 4, 6, this is page 92, right? So every single curve that you have, that corresponds to this ratio right there, right? RL over Z naught. Okay, so per given RL over Z naught, you can see we have the ratio of the frequencies will be that will be a function of the ratio of the voltages, and we can make use of this to approximate the average output voltage of the resonant converter, right? So let's look at an example here. We have ZCS, right, with the following parameters: 12 volts input, resonant is 0.1 micro, inductor 10 microhenries, I out is 1 amp, switching frequency 100 kilohertz, right? And then part A, determine the average output voltage of the converter, determine peak current in L and C, and what is the required switching frequency to produce an output voltage of 6 volts, determine the maximum switching frequency, and if the load resistance change, right? So basically we are changing the output current by doing this. Determine the switching frequency, the new switching frequency. Remember I said earlier that in order to adjust the output voltage, you're gonna need to change the switching frequency. So let's do this problem. Right, I have the answers and I use MATCAD to do this because I'm too lazy to do it by hand. So those are the given values, right, stated in the problem statement, right? And then from there, I could get resonant frequency in radian per second. That's our omega, right? And then there's the characteristic impedance, right there, 10 ohms, right? From the given values. And then part A, determine the average output voltage. So I'm using the actual or exact equation, right? So in order to do that, I need T1, I need to calculate the different times, T1, T2, T3, right? And from the given values, I get all those values for T1, T2, and T3. T1 is right there, T2 is right there, T3 is right there. And then eventually I have the average output voltage equation, right? I just rewrite that here. And you can see that by per given values, right? Like those are above here, right there. Then I get output voltage equal to 7.688 volts, okay? Any question on this? So again, part A, I'm using the exact equations. In order to do that, I have to calculate T1 through T3, right? And then from there, I can get the output voltage. All right. And then part B, determine peak current of L and peak voltage of C. We learned from the second state, right? When we have this resonant converter, resonant circuit, I should say, that the peak of the capacitor voltage is twice the input, right? So that's what I have right there, it's twice the input. So that's 24 volts. Again, that's coming from one of the equation I have in the derivation of CR and LR, CR voltage and LR current. And we just saw this equation earlier, right? That the peak value of the inductor current is the offset, right? Plus Vs over Z naught, right? That's going to be 2.2 amps, right? Any questions so far? All right. Now determine the switching frequency if V out is to be 6 volts. So rather than 7.68, let's say I want to change that output voltage to 6 volts, right? Well, I could do that by changing the frequency, right? So what I did here is that from the average output voltage equation, I just solved for F instead of solving for V, because V is given here, right? Output voltage is given, right? And so by doing so, I get the switching frequency that is required to get V out for the same I out, right? So this is the same I out. So I get 78 kilohertz roughly, right? Or by using this equation is 78.043 kilohertz to get 6 volts. So that's from the exact equation. What about from the graphical method? Using the R plot, we have to determine the ratios first, right? So first, I need to find the load resistance, right? That's going to be V out over I out. V out is given, that's 6 volts. I out is given to be 1 amp. So therefore, RL is 6 ohms, right? And then from here, I get the ratio of RL over Z naught. That's 0.6 right there. Right, so that's the first ratio we need. The second ratio, depending on what's given in the problem, in this case, I get the second ratio from the voltages, right? Because output is 6 volts, input is 12 volts. So I get the second ratio, which is 0.5, V out over Vs, right? And then I do have the resonant frequency right there. Remember, I found omega. So if you divide omega by 2 pi, I get resonant frequency in kilohertz. Right? So the only one that's missing is the switching frequency, and that's what this method is. That's what this method can give you, right? Instead of using exact equation right there to find switching frequency, you can also do the same thing, estimate the switching frequency using these ratios. Okay. All right. Let me get this smaller so you can see what is the first one. We can see that the R ratio is 0.6. The given curves that I had earlier doesn't have 0.6. I have 0.5, 1, 2, 4, 6, 10. So this is where you're going to have to estimate where 0.6 is going to be. So I'm going to estimate that 0.6 curve to be right there, slightly below 0.5 and above 1. Okay, that's just an estimation for 0.6. Right? That's why it's an estimation. It's not an exact calculation. Right? So that's for 0.6. Any question on this? All right, and then I have another ratio, that's voltage ratio, that's 0.5. So if you look at the x-axis, that's the ratio of the voltages. So find 0.5 right there, right? And then you just draw a straight line up until it intersects with the 0.6 curve right there, right? Then once you find the intersection between the 0.6 curve to the 0.5 line, then just go straight across to give you the ratio of the frequencies right there. So roughly for this problem, you can see that the given 0.5 ratio of the voltages and 0.6 for the ratio of the load resistance to characteristic impedance, you get ratio of frequency to be equal around 0.48, right? That's what I use, 0.48. Roughly 0.48. Okay. So now I know the ratio of the frequencies, right? 0.48. How do I use that? Well, I know that the ratio is defined to be Fs over F naught, right? Fs over F naught. So if Fs over F naught is 0.48, then Fs is equal to 0.48 times F naught, right? And we know F naught? Yes, that's this frequency right there. So from there, I get the required switching frequency, which is what? Around, I said right here, or I wrote right there, 76.4 kilohertz, right? So from a graphical method, I estimated the required switching frequency to be 76.4 kilohertz. From the exact equation, I get 78.043. Not bad, right? Not bad at all for estimating the switching frequency, 78 versus 76. Any questions on this? So hopefully that would demonstrate how you would use the graphical approach. Any questions? And then part D, determine maximum switching frequency. We learned from last week that would be determined by time T3, right? So T3 is special because I would define our maximum switching frequency. So that's going to be 1 over T3, gives you 146 kilohertz for this problem. And then the last one is going to be long, right? Because we are changing the current. Right away, if you, after you learn about the equations for the circuit, you know right away that if you are changing load resistance, that means you're changing current, output current. If you're changing output current, then output voltage is going to change as well, right? So, and then here, output voltage given, which means you're gonna have to find the new switching frequency, right? And in order to do that, since output current changes, so do the times right there. They also will change. So now we have the new T1, new T2, new T3. That's why I like to use MATCAD, because I just, copy paste the equation and I got the answers right away. And then, copy paste the equation for switching frequency, and I get the new switching frequency of 70.349. So by changing the output current and for a given voltage, you can get the required switching frequency. Any questions on this? No? All right. If not, let's move on to our next one. I'm going to go through this rather quickly, right? It's going to be the same type of assumptions, right? That we have the load side, right? Being what? Being modeled as a current source right here, right? So that's our assumption, just like before. We assume ideal components. We assume unidirectional switch, right? But notice that we have our resonance circuit right here, right? But in addition to that, we also add diode that has to be connected that way to make this work. Okay. Now, what I can see from here, what I can understand from this circuit is that since we have resonant capacitor and then diode across the switch, therefore these three components share the same voltage, right? And then the circuit will provide you with zero voltage switching, right? Now, from strategy, if you look at the strategy to achieve this, right, you could kind of take a guess, right, from the way this circuit is connected, these components are connected. And since I have resonant capacitor in parallel with the diode, in parallel with the switch, so I know that anytime this capacitor voltage goes to zero, right, then that would allow this diode to conduct, right, that way, right? Then as soon as the diode conducts, assuming ideal, then voltage across the diode is zero, right, as well, right? So as soon as we are depleting the energy through this capacitor, then voltage across the cap is zero, right? No more to discharge. And then that voltage will also appear across the diode, right? Forcing the diode to turn on or conduct current, right? As the diode is conducting current, right, and voltage is zero across, right? Therefore, voltage across the switch is also zero. Now you can see, oh, that must be the key here, is that if I can somehow have the diode conducting after the capacitor there fully discharges, then that will be perfect timing for us to either turn on or turn off. I think in this case, you turn it on. You turn on that switch at zero voltage, right? That's how you get the zero voltage, right? So that's kind of like the strategy, and see how we can implement that strategy in this circuit, okay, by looking at the 4 different states, okay? All right, so the same thing, 4 different states. How do we get 4 different states? We have 2 switches, right? The main switch and the diode. Also, note that output voltage is right here, right? That's V out across the load. You can see that output voltage is equal to voltage across the diode, this diode right there, this diode right here. Right? You can see they're in parallel, right? So therefore, later on, when we derive average output voltage, we're going to take a look at the equation for Vx, for voltage across the diode. And if you find the average of Vx, then we can find the average of V out, because that's the same voltage, okay? Just keep that in mind. Okay, so let's go over the states. 4 different states, 2 different switches, right? So 4 different possibilities. Switch is off, diode is off, switch is off, diode is on, switch is on, diode is on, and then switch is on, diode is off, right? 4 different states. assume it's already running in operating steady state. So it doesn't matter where you start the analysis. I'm going to start the analysis from here, from this state right there. Let's call it state number 1, where both the switch and the diode are off. Okay. If that is the case, imagine, right? Let me erase all of these. If the switch is off, right, and then the diode is off, then what's going to happen? Well, we are forcing this load current to flow through the big loop, right, going back to the source, right, and then it must go through the cap right there, right? Why can't it go to the diode? Well, the diode is pointing from right to left, right? So current cannot flow from left to right, right? That will be blocked by the diode. And why not go through the switch? Well, as I said earlier, at this point, the switch is open or off, right? So therefore, the only path that is possible for this output current to flow through is, or to flow around the loop, is through the cap right there. Okay, it goes right here and back to the load right there. Any question on that one? Now, let's see if we can answer this quickly. If I were to ask you, what is the voltage across the inductor at this point? If this is an in-class person, I'm gonna, you know, I bring candies with me. Whoever can answer the first time, I give you the candy. So what is the voltage across that inductor? Come on, quickly. Don't look at the waveforms, because that would be cheating. What is the voltage across that inductor? Anybody?
I know.
Voltage, not current. What is voltage across
Yes, minus VC.
Say it again?
Sure, just please.
VS minus VC minus VX.
Okay,
Or
that's,
parentheses. Oh, did I miss a parenthesis? I don't know.
no, it's fine. You're applying KVL, but there's a simple answer to that.
VS.
It's not VS. Look at the current that goes through that inductor. What kind of current is it? Is it a changing current or is it a constant current?
Oh, 0 because I was
Zero,
constant.
Yeah, yeah.
There you are. There you go. All right. So now you know that that's why I didn't draw. I didn't actually label, because I know that, you know, current through the inductor is I naught, which is constant. So we know that if there is a constant current flowing through inductor, that means voltage across is 0 volts right here, right? How? VL is equal to L DIL dt. So don't forget VL is equal to L DIL dt. So if DIL dt is 0, because we have a constant current, therefore voltage across the inductor is 0, right? If that is the case, then KVL states that voltage across the supply right there is equal to VC plus VX, right? Agree? All right. Now that's the first question. The second question is, again, don't look at the waveforms, okay? On the next page. If I ask you, can you determine the shape of the voltage across the cap right there? What will be the shape?
Linear?
Linear. Is it increasing or decreasing?
Decreasing?
Decreasing.
Because IO is flowing out of it, out of its negative terminal.
If you have a cap right here, and then that's the positive side of the cap.
Oh, wait, it's increasing.
Okay, okay. All right, so the current flows into the cap, so therefore we are charging that capacitor, right? How are we charging that capacitor? Linearly. How do I know it's linear? Can anybody answer that?
Current's constant because it's in series with the inductor and the current source.
That's correct. So, well, why is it that when current through the cap is constant, can you show me the mathematical equation that proves that's actually a constant slope, linear slope on the voltage?
I equals C dV dt.
Very good. So I know that for a capacitor, IC is equal to C dVC dt. So therefore, dVC dt So therefore, dVc dt is equal to IC over C. But in this case, IC is equal to I naught, right? Constant, right there. So I know that the slope of the voltage across the cap is equal to a constant value, positive constant I naught divided by positive constant CR. So that's going to give you positive constant slope right there, meaning linear slope, okay? Any question on this? As you can see, this is kind of similar to the previous circuit, right? The same type of analysis, okay? And then what happens next? Well, I know by KVL, this is going to be 0 across the inductor, so that doesn't matter, right? From the point of view of KVL. So I know that's going to be Vs is equal to Vc plus Vx, and I know that Vc Vc is increasing with time, right? So this Vc is increasing with time, right? And then as Vc is increasing, because Vs is constant, therefore to compensate for the increasing Vc, Vx has to decrease linearly. So if I ask you to draw waveform across Vx, it should be decreasing right now from Vs, right? So at some point of time, right, as you are letting this capacitor voltage to charge, right, increase linearly, at one point of time, voltage across the cap will be reaching Vs. You agree? At some point of time, Vc is going to be equal to Vs. If that is the case, then Vs is equal to Vs plus Vx, right? So therefore, Vx is equal to 0, right? So as we are letting this capacitor voltage to increase linearly, at some point of time, it will reach Vs, right? Vs, and when that happens, Vs, when that happens, then automatically that would turn this diode on, because now voltage across the diode is 0. That's how we change. That's how the circuit changes its states from state number 1 to state number 2, right? Now diode turns on. Okay. Any question on that one? Now, once the circuit state changes to number 2, right there, then what can you see here? What kind of circuit do you have here? Beginning of the chapter. What do you call that circuit? Start with R.
Resonant circuit.
Resonant circuit, yes. One of the circuits that we went over beginning of the chapter looks exactly like this, right? Where you have a series of the supply and then capacitor and inductor, and the whole thing is in parallel with the current source. So this will give us resonant circuit. What's so good about resonant circuit for this type of to achieve this zero current switching or zero voltage switching? What's so good about that? Well, we learned that if you have resonant circuit, that means inherently capacitor voltage now is going to be sine wave, and inductor current will also be sine wave, right? As soon as we have resonant circuit. So if you go to the following page, right? I'm not going to draw this. It's already here. So you can see that as soon as I start the cycle, right? We have the first state, right? That's linear across the capacitor, as we talked about earlier. And then voltage across the inductor is going to be 0. But if you look at the current through the inductor, right here, it's going to be I naught, right? It's going to be constant current I naught. So that's why on the inductor current, right here, that's inductor current right there, right? Resonant inductor current. You can see when we start the analysis, right? Inductor current is equal to I naught, right there. Okay, and then that happens until capacitor voltage reaches Vs right there, right? After which we have state number 2, and state number 2 we know is going to be resonant, right? So then naturally capacitor voltage now is sine wave, so following sine wave from linear to a sine wave, and then the same thing as the inductor current. But you can see that the reason why this is good, because now we have a sine wave that would naturally goes to 0, right? Voltage across the cap will eventually go to 0, right? So let me erase this, erase that. So right here we have resonant circuit, and we can see that voltage across the cap start to be sine wave. Same thing with current through the inductor. The inductor. Now, let's look at this inductor waveform further, right? Notice that the equation now for KVL is equal to VS is equal to VC plus VL, right? You agree? KVL around this loop, right? The diode is 0 now. So Vx is 0 already, so that doesn't matter, right? Okay, so now what do we know about Vc with respect to Vs? At this point, what do we know about Vc with respect to Vs? Anybody?
In the beginning, they're equal, but then it decreases.
And then Vc is going to decrease? Why? No, right? It's going to keep increasing. There's nothing to tell it to decrease, right? So as soon as it reaches this point, right, it will still continue to charge, but it's following a sine wave, right? So what I'm saying is that as soon as the state changes to this state, right, this capacitor still wants to increase its voltage following a sine wave, right? And in order to do that, there's nothing to stop that voltage to decrease, right? It will keep increasing, but now it's following a sine wave, so we know at some point of time it will decrease. But at this moment, it will still, because it's following a sine wave, it will still increasing, right? Following a sine wave, right? That means, right? Remember that this state occurs when Vc is equal to Vs, right here. That's your Vs point, right? So that means as this capacitor voltage is charging more, right? Voltage across Vc must be larger than Vs. Right? You can clearly see from here. Right? So after Vc is equal to Vs, its voltage keeps increasing above Vs. You see that? Following a sine wave. So that means if you apply that to this KVL, what does that mean to VL?
It's negative.
It's negative, exactly. So therefore, the actual polarity of the voltage across the inductor is actually minus plus. What does that mean? If current flows from left to right, but then the inductor voltage is minus plus that way. What does it mean? If you're the inductor, what are you doing now?
Current's decreasing.
Discharging, right? It means it's discharging, right? Because now we know that the polarity of the inductor is minus plus that way, and then the current flows into the negative side of the inductor. Therefore, we know that at this point, the inductor is discharging, right? That's why if you look at the inductor current, right? Again, I simulated this just like the first circuit. I simulated this with PSpice, so this is not waveforms that I drew myself, right? This is from PSpice. You can see clearly that as soon as Vc is equal to Vs, current on the inductor start to decrease, following a sine wave, right there, right? So now you know the reason why this is decreasing, because voltage is negative across inductor. All right. Any question on this?
I had a quick question.
Yeah, go ahead.
How do you know it's sinusoidal to begin with?
It's resonant.
That VC is going to.
We know for sure because this is a resonant circuit, right? Beginning of the chapter, we have this circuit. We analyze.
Oh, the topology, yeah.
Right. Exactly this circuit. So we know anytime you have this circuit, you're going to have resonance. That's how I know it's going to be sine wave. Does that answer your question, Nick?
Yeah, that makes sense. I just recognized the short
Okay.
that's coming out. Yeah, thank you.
And of course, in the beginning of the chapter, we looked at the equations, right? And we found out that the equation for the inductor current is sine wave. The equation for the voltage across the cap is also sine wave, right? Because again, this is resonant circuit. All right. Any other questions? Okay, so now let's see what's happening here. We have voltage across the cap that goes sine wave, right here. I'm just going to show you the picture here, right there, right, follows the sine wave, right, and then it's going to reach its peak value, and then now it's going to start to come down, meaning now the capacitor is discharging, right, because the slope is negative right there. So I know that starting from the, right after that peak value, the capacitor start to discharge, right? And then you can see that that happens when the inductor current reaches zero, right? If you look at the timing, when the capacitor voltage reaches peak value, that happens when the inductor current reaches zero, right? Does that make sense? Why? Well, you can take a look at the circuit again, right here, right? As soon as IL is equal to I naught right here, right there. So what can you say about, actually, no. That happens when IL is equal to zero, not I naught. My bad. You can see that, that happens, the peak value right here occurs when IL is equal to zero amps, right? You agree with that statement? That's 0 amps right there. Okay, so now it means that you get the peak value of this capacitor voltage, right? Let me erase. This voltage right here is reaching its peak value when current is equal to zero, right here. So you can see that IL is equal to IC. Does that make sense why it's reaching the peak value when current is equal to zero? To me, it does, right? Because right here, right? That equation right there, dVc dt is equal to IC over C. At this point, IC is equal to zero, right? That same current, zero current flows through the cap. So if inductor current goes to zero, so is the capacitor current. So if capacitor current goes to zero, so go ahead and put zero right there, then you can see that dVc dt is equal to zero, right? So that means the slope of the capacitor voltage is zero. So that tells us that that's the point where capacitor voltage reaches its peak value. Any question on that one? Right there. Okay. Okay. No questions? Now, this is what's interesting. This is different from the previous circuit in a way that you can see that we are allowing current through the inductor to go negative, right? Because it follows a sine wave, right? It follows a sine wave and it goes to zero, but then it continues to go to negative. And that is allowed in the circuit, not like the previous circuit. In the previous circuit, we clamped that to be zero, but here we allow it to go negative. That means, right, this current right here, right? Erase this, erase this, erase this, right? This current right here, right, changes direction, right, following a sine wave. So initially it goes from left to right, and then after it passes zero, current now goes from right to left, right? Now think about it. If the current through the inductor is going from right to left, right, following this path right there, what does that do to that capacitor? Anybody?
Discharge.
Discharging, because now capacitor current's leaving the positive side, right? So as soon as you can see clearly from this picture that as soon as current, inductor current crosses zero to the negative side, swinging negative right there, right? As soon as the inductor current, which is the same as capacitor current, goes to negative, that means we are forcing the capacitor to discharge. You see that negative slope right there? So now it's discharging, following a sine wave. Until when? Well, until we keep doing that, right? Until the energy in the capacitor is depleted, fully depleted, right? So we keep discharging this cap until the energy in the cap is gone, right? Or depleted, I should say. Now, once that happens, what happens with the voltage across the cap if it's fully depleted? What's going to happen with the voltage across the cap after we fully discharge the cap? Equals?
It goes to zero, right? Because that's the goal of switching.
Exactly, zero voltage, right? So as soon as you fully discharge that cap, automatically, right, that capacitor voltage is going to be equal to zero. right? No more energy to be discharged there, right? But then this current is still is negative. You see that current is still negative. You look at the waveform here. Even after the capacitor voltage equals to 0, right? We still have negative current. See that? Current is still negative. It's not 0. So I know that at that point, once that capacitor is fully discharged, I still have negative current. But that negative current cannot flow through the capacitor anymore. You agree? Because there's no more charge left in that capacitor. So where does that current flow then? Where does that negative current flow? If
The diode.
The diode, yes. So that's what's wonderful about this, and it's almost like magic. To this day, I'm still amazed with how the circuit works. Because as soon as the current flowing to negative, right, and then capacitor said, okay, I'm done. I don't have any more charge to discharge myself, right? Then current will have to be flowing through the diode. Right? Once this path is done, then the negative current must flow through the diode. Okay, any question on that one? So now the state changes to this state right there, because now we have a short across the cap, right? So imagine you have a short across the cap, so that means these capacitors practically disappear from the circuit, right? That's why the state changes from this state to this state right here. Does that make sense, hopefully? Okay. All right, if that's the case, again, assuming diode is ideal, as I said earlier, every component is ideal, right? So now we have 0 volts across that diode. Then we have this circuit right here, okay? Right there. Now what's gonna happen here? Well, now we don't have any more resonant circuit, right? The capacitor is gone, so you only have inductor. So no more resonant circuit. How do we prove that? Well, I know if you do KVL around this loop, you can easily find out that voltage across the inductor is equal to Vs, right? Because that's going to be 0 volt right here, 0 volt right there. So therefore, by KVL, voltage across the inductor is Vs. What does that mean in terms of current through the inductor? It means that VL is equal to L DIL dt, right? So therefore, DIL dt is equal to VL over L. Right now, VL is equal to Vs divided by L. So what does that tell you? Well, I know that at this point, in this state right there, right, voltage across the inductor is positive, L is positive, so therefore the inductor current will be a linear current, right, increasing linearly. And that's what we are seeing in this waveform right there. Now, hopefully it makes sense. Why is it that right after capacitor voltage goes to 0, see right after this point, you can see that inductor current now is linear. See that? It's now linear. Okay? Increasing, still negative, but now it's increasing. Before it was following a sine wave, and then as soon as capacitor voltage goes to 0, it changes the state of the circuit. Now the circuit is no longer a resonant circuit, so therefore now inductor current now changes to linear change instead of sine wave, based on L DIL dt. Any question on that one? Okay, now this is where we want to take advantage of the circuit, right? Because I know that at this point in state 3, right there, I know that the diode is conducting right here. This diode is conducting. If that diode is conducting, voltage across the diode is 0 volt, right? At this point, the switch is still open, right? It's still off right there, right? So why not take advantage of this, right? Because I know that as soon as diode is conducting, voltage across the diode is pretty much 0. And that means because the two are in parallel, right? Switch and diode they're in parallel. Therefore, voltage across the switch is also equal to 0, right? As soon as diode is conducting, voltage across the switch is also 0. So now we have 0 voltage across the switch. The switch is still off, but its voltage is 0. So why not take advantage by turning on that switch, right? As soon as the diode is conducting, that's a perfect timing for us to turn the switch on at 0 voltage. Okay, is that clear? the statement that I just made. As soon as the diode is conducting, then we're going to turn that switch on right there. Now you have two sources, right? Any question on that? So now we are turning on the switch at 0 voltage right here. So right, you see this pulsing, the pulse that I have there. So right after the diode is conducting, I turn the switch on at 0 voltage. Right. Now what's interesting about this is that at this state, right, I have the switch conducting, not conducting, sorry, on, right, at this point. And then diode is also on, right, like this. The capacitor is done, right? The capacitor right here is done. So I'm not gonna bother with that. But if you look at this state right there, you have the switch that is right now on, and then diode is also on. If you look at this point right there, right, can you tell me which one is actually carrying current? Is it the diode? Because the two are in parallel, right? We have diode that is on and we have switch that is on, but only one is actually carrying current right now. Which one of the two? At this point. Let's say at that point. Which one is actually carrying current? Is it the diode or the switch? The switch is already turned on. But is it carrying current? Is the switch carrying current at this point? Remember, the configuration is like this. Right, so now we have this this way right here, right, where the diode is conducting. So at this point right there, is the switch carrying any current or no? The answer is?
Yeah.
The answer is no. Why not? Because the switch is unidirectional, right? Just like the previous circuit, right? So the switch can only carry positive current. It cannot carry negative current. Right now, the current is still negative, right? That current right there is still below 0. So even though the switch is already on, right there, but it's not carrying current. Current still flows through the diode that way, right? Because why? Well, because it's a negative current. Current flows from right to left, right? Agree? Now, when does the switch take over the current? Anybody?
Once it's positive.
Exactly, because remember that inductor current is now increasing linearly. It is still negative right there. So as soon as, or as long as I should say, as long as inductor current is negative, then even though the switch is on, current will flow through the diode. Right? Only when the current through the inductor is positive right there, right? Right here, that now the switch takes over, right? So now when the current through the inductor is positive, going from left to right, now we have the diode off automatically, right? Because it cannot provide, current from left to right. The capacitor is off also, and now the only component that's conducting current is the switch, right? Until when? Well, you can see that since the inductor current increasing linearly, at some point of time, that inductor current will reach I0, right? This is growing and growing and growing until this current is equal to I0. What happens when current is equal to I0? Automatically, diode will be off because it cannot provide current downward, right? It tries to go, IL tries to go above I0, right, by trying to find a path, but there is no path other than the diode, right? If you look at the original circuit, there is no other path right here. So the only path to go down is through the diode, but the diode cannot handle that because the diode is pointing upward. So therefore, when IL tries to go above I0, it can't, right? Because diode is off. And so now the state changes to this state right there, where the diode is automatically off. And then you can see that IL is being clamped to I0. So you can see that IL grows, right, linearly, but then it stops at I0 right there. So it's being clamped by the source, by the load. Okay, and then what happens? And then after that, you have the last state right here, right? And then this state is going to keep continuing until you start the cycle again, until you start from the beginning again, start from here again, when you turn off the switch. Okay? All right.